This is the second mini lecture for section 4.1 of the textbook. So every number is divisible by 1 in itself. Some numbers have only those divisors. For example, the rainbow diagram for the number 37 is very simple. It's just a 1 and a 37 connected with a line, because there are no other divisors in between there. So a whole number greater than 1 is called prime if it's like 37, if its only factor pair consists of 1 in itself. Okay, a whole number greater than 1 that's not prime is called composite. Composite just means not prime, but of course what that means is that it has more factor pairs than just 1 in itself. The number 1 is called the unit. It is neither prime nor composite. So just remember, 1 is not prime. If you forget that, that'll confuse you on things later on. So for example, 37 is prime, 60 and 36 are composite. Now, every whole number greater than 1 can be written as a product of prime factors. Okay, and it'll turn out that there's one and only one way to do that, and that product, that factorization, is kind of like the DNA for the number. So for example, consider the number 2100. So we have 2100, which is equal to 21 times 100. 21 is 3 times 7. What I'm making here is called a factor tree. 3 and 7 are both prime, so that branch of the tree stops there. 100 is 10 times 10. 10 is composite as well. 10 is 2 times 5. And 2 and 5 are prime. So we end up with 2100 equals 3 times 7 times 2 times 5 times 2 times 5. Now, one thing we might worry about in doing this is the possibility that the list of primes we get might depend on the choices that we made. So for example, when I started here, I factored 2100 as 21 times 100. Of course, that's not the only way to factor 2100. So we might wonder if I made different choices as I went down the tree, whether I'd get a different list of primes at the end. For example, when I start with 2100, instead of doing 21 times 100, I could do 30 times 70. Okay, and 30, let's see, it's 5 times 6, and 5 is prime. 70, let's do 2 times 35. Now 2 is prime. Now 6 is composite. 6 is 2 times 3. Both of those are prime. 35 is 5 times 7. And 5 and 7 are both prime. So this tells us that 2100 is 5 times 2 times 3 times 2 times 5 times 7. So what we see is that, I made different choices as I went through the tree, but I ended up with the same list of primes, which was a pair of 2s, a 3, a pair of 5s, and a 7. Okay, and the fact that we can always do that is so important. We call it something, we call it the fundamental theorem of arithmetic. So this is the most important theorem in arithmetic. Every whole number greater than 1 either is prime, or it can be written as a product of primes. And this factorization is unique, apart from the order of the factors. We can use the prime factorization of a number to answer questions about divisibility and all sorts of things. For example, consider 600. 600 is 10 times 60. 10 is 2 times 5. 60 is 4 times 15. 4 is 2 times 2. 15 is 3 times 5. So we have, let's see, 2, 5, 2, 2, 3, and 5. So 600 is 2 times 2 times 2 times 3 times 5 times 5. Or in other words, 2 to the third power times 3 to the first power times 5 squared. So let's use that to answer some questions. For example, is 600 divisible by 75? So to answer this, I don't want to perform the division by hand. I don't want to use a calculator or long division or anything like that. I just want to use the prime factors. 75 has the prime factorization 3 times 5 times 5. Now, when I look inside of 600, I can see the 3, the 5, and the 5. So the answer here is yes. 600 contains a 3 and 2 5s as factors. Okay, or again, let's ask the same thing for 45. Is 600 divisible by 45? Well, 45, what's 9 times 5? That's 3 times 3 times 5. And so again, I want to try to find this in 600. Now the 5 is fine, here's a 5. And I can also see one of the 3's. But 45 has 2 3's, and 600 only has 1. So the answer here is no, because 45 has 2 3's, but 600 has only 1. Or again, is 600 divisible by 24? And on second thought, just to clarify something, let me not do 24. Let's just do 12. 600 divisible by 12. Well, 12 is 2 times 2 times 3. That's its prime factorization. When I look inside of 600, I can see a 2, a 2, and a 3. So the answer is yes. I can see the 12 inside of there. So yes, 600 has 2 2's and a 3 in its factorization. So again, we're just trying to see if we can find those prime factors in the factorization of 600. And this is an idea that comes in very handy when you are working with fractions. And often a discussion about divisibility like we're having now would go before fractions in later elementary grades or middle grades. Now, we can do a lot more than that. We can do more than just answer questions like that. We could actually list all the divisors of 600. So it's a little tricky, but the main idea is this. Every divisor of 600 has to be made up out of these primes. These are like the building blocks we have to work with. So if I could list every number I can build up as products of some of these primes, I will be listing every divisor of 600. Of course, I always have to include 1, because that's always a divisor. So let's try to do this systematically. Let's begin with just the 2's. Forget the 3 and the 5's. what numbers can I build up out of the 2's? Well, we have the number 1, of course. We should always start with that. But then we have the number 2. Let me move this over a bit. The number 2, and then 2 times 2, and 2 times 2 times 2. And that's all the numbers I could build up out of 2's. Now let's throw in the 3. What are all the numbers I could build up using those 2's and a single 3? Well, I could figure that out by just multiplying all of these by the 3. So I'd give us 3, 2 times 3, 2 times 2 times 3, 2 times 2 times 2 times 3. Let me box these, and you'll see why in a moment. But yeah, for now, suffice it to say that these are all the numbers I can form from the 2, the 2, the 2, and the 3. Now suppose I use the 2's, the 3, and a single 5, exactly 1 5. Well, to list all those, I could multiply all these by 5. So I'd have 5, 2 times 5, 2 times 2 times 5, 2 times 2 times 2 times 5, 3 times 5, 2 times 3 times 5, 2 times 2 times 3 times 5, 2 times 2 times 2 times 3 times 5. Okay, so there's a second block of numbers. Okay, the third block I can get by multiplying by that second 5. Now I was going to try to squeeze it here, but I ran out of space, so we'll just put it below. Let's see, we have 5 times 5, 2 times 5 times 5, 2 times 2 times 5 times 5, 2 times 2 times 2 times 5 times 5, 3 times 5 times 5, 2 times 3 times 5 times 5, 2 times 2 times 3 times 5 times 5, 2 times 2 times 2 times 3 times 5 times 5. Yep, so these are all the numbers I could form out of these primes. See, there's 24 in all. Those are the 24 divisors of 600. And yeah, hopefully it's clear that if we were to try to use a rainbow diagram to list all these for 600, that might take a while, and it would be easy to miss things. If we were systematic, this might be a better approach sometimes. Okay, more generally though, we can use that prime factorization to determine how many divisors there are before we actually list them all. So if we think back to this example, see, we had 3 2x4 blocks. So the total number of divisors is 2. It's 4 times 2 times 3. 4 times 2 times 3, which is 24. Okay, now looking ahead of it, I could have figured out that we'd have these 4x2 blocks because we have 2 to the third and 3 to the first. And we'd have 3 of those blocks because it's 5 squared. So let me explain. So if n is a whole number with the prime factorization like so, then you can figure out the total number of divisors of n by adding 1 to all of those exponents and multiplying them together. For example, how many divisors does 84 have? 84 is 21 times 4. 21 is 3 times 7. 4 is 2 times 2. So therefore 84 is 2 squared times 3 to the first times 7 to the first. So if I add 1 to each of those exponents, That's 3 times 2 times 2, which is 12. So 84 has 12 divisors. Okay, and you see, I'm able to do that without actually listing them all. And this is a powerful idea. On an exam, if you're asked how many divisors a number has, but you're not asked to list them all, then don't try to list them. Sometimes that's really hard to do. Instead, use the prime factorization together with this formula. So the example asks us to list them. I'm not going to do that right now because it's very similar to the last one, but it's something to try to do for practice, and we'll talk about it on the homework as well.